Hello everyone, my name is Tolga-Can Çallar, and in this video I will be presenting our paper titled Hybrid Learning of Time Series Inverse Dynamics Models for Locally Isotropic Robot Motion. Inverse dynamics models that can predict the torques that occur within a robot's joint due to the executed motion are fundamental for many applications in the fields of force control and motion planning. With the advent of multi-articulated robots, as the KUKA EVA 40 shown here, that are increasingly employed in real-world tasks, there is an increased demand for inverse dynamics modeling strategies that can accurately represent the high-dimensional dynamics of kinematically complex robots. Looking at a general formulation of robot dynamics, a large portion of torques results from static gravity, inertia, and Coriolis forces as a function of the joint angles and their temporal derivatives within the framework of rigid body dynamics. Due to the presence of effects that exceed the assumptions of rigid body dynamics, such as complex friction and joint flexibility, we also have to include a collective term epsilon to account for such additional phenomena. In fact, these non-rigid effects that may depend on an indefinite number of variables can significantly contribute to the overall dynamics in many applications in the areas of collaborative, medical, and social robotics. In such cases, the executed robot motion is often comprised of segments of low velocity and frequent reversals of the joint-wise directions of rotation within small angular intervals. This can, for example, prevent the saturation of mechanical deformations of various internal components, leading to an increased influence of nonlinear hysteretic dynamics associated with low-velocity friction, joint flexibility, and backlash. As shown by the formation of joint torque hysteresis loops in this figure, joint torques substantially depend on the rotation history, which itself is consistent with mechanical hysteresis. In this context, we introduce and characterize a novel robotic motion type that we call locally isotropic motion, or LIMO for short. LIMO represents a class of motion tasks that provoke a wide spectrum of dynamic states by being composed of dynamically contrasting subsequences. On one hand, LIMO contains segments of joint-wise large-scale motion over large angular intervals with moderate velocity and acceleration and consistent rotation directions. This may correspond to gross motor subtasks, the dynamics of which are largely governed by rigid body dynamics and simple friction. Secondly, LIMO contains segments of joint-wise small-scale movements with low velocity and acceleration, corresponding to the execution of fine motor subtasks. Most notably, the joint-wise direction of motion is frequently changing within small angular intervals. This results in an isotropic movement pattern, in analogy to randomized explorative movements and reactive motion compensation. In the context of inverse dynamics modeling, LIMO-like motion introduces significant torque contributions that result from non-rigidity and the system's dynamic state history, which are difficult to model by conventional approaches. Although previous works comprise a wide spectrum of approaches, ranging from parametric model identification over non-parametric and neural network-based model learning to even gray box modeling strategies, none have been developed for LIMO-type dynamics. Thus, the central question that we address revolves around the optimal model architecture for the inverse dynamics modeling of LIMO dynamics, considering its key properties and being composed of dynamically contrasting motion sequences and the amplified influence of time dependency effects such as torque hysteresis. For this purpose, using a KUKA EVA 14 robot with integrated joint torque sensors as our experimental platform, we propose a hybrid model learning architecture that combines a rigid body dynamics model learned by parametric identification with data-driven model learning using neural network topologies based on multi-layer perceptrons and time series networks in form of LSTM and transformer architectures. Initially, we apply a parametric identification procedure based on the Newtonian formulation of mechanics to obtain a rigid body dynamics model. The model is identified by statistical regression of the inertial and simple frictional link parameters from dynamic measurements made during the execution of optimized sinusoidal excitation trajectories. Given a series of joint angle measurements Q and the respective time derivatives, and the kinematic structure of the robot K, the rigid body dynamics model provides torque predictions that are fed forward for the downstream summation with the neural network predictions. However, at the same time, the downstream neural network component itself accepts the rigid body dynamics model predictions as an auxiliary input along with the joint angles, velocities, and accelerations to generate the final hybrid model predictions. Regarding the specific neural network topologies, we investigate various configurations, including a multi-layer perceptron ensemble, where each MLP predicts one joint prediction respectively. Also, we evaluate time series topologies that accept a series of joint motion measurements to leverage temporal sequence information, such as consecutive LSTM cells, an LSTM cell with a distal fully connected layer, and the transformer architecture. To further exploit time series information, we introduce a novel rotational history encoding as an additional neural network input feature. It is defined as the joint-wise rotation angle since the last reversal of rotation direction at a given moment. The rationale here is to create an input feature that reflects the state of hysteresis with respect to the rotation history of a particular joint, allowing to either guide the inherent sequence learning capabilities of, for example, recurrent neural networks, or even encode temporal information into non-recurrent architectures, such as the multilayer perceptron. For our training data, we compute random collision-free scaffold configurations and generate LIMO-type motion trajectories around those by partitioning motion paths into two phases. In a linear reaching phase that you are seeing right now, a joint-wise linear trajectory is executed to reach the next scaffold configuration, the pose of which is denoted here by the red dot. Afterwards, a sinusoidal exploration phase is initiated locally around such a configuration. Here, joint-wise independent and randomly parameterized sinusoidal trajectories with low amplitude are executed. This yields a motion sequence with intermittent segments of isotropic motion, with the goal to provoke hysteretic dynamics throughout the configuration space. These LIMO-type paths are executed around 150 scaffold configurations, spanning a hemispherical workspace yielding approximately 300,000 recorded path points on which the hybrid models are trained. The training data densely cover both a large Cartesian and dynamic state space, including dynamic states with multiple combinations of joint angle, speed, torque, and rotation angle since the last motion reversal. The performance of the proposed model architectures and their variations are evaluated comparatively by training various model configurations on the LIMO dataset employing a 80-20 split. The models are further validated on a separate dataset acquired during the execution of a sequence of large amplitude sinusoidal excitation trajectories with decreasing base frequency to obtain non-LIMO dynamics for comparison. Additionally, an ablation study is conducted by removing the network connections denoted by the dotted lines, such that both hybrid and standalone model variants are evaluated and the effect of the rotational history encoding can be isolated. On all datasets, models trained in hybrid configuration consistently achieved lower mean squared errors than their standalone counterparts, where the hybridization of MLP7 and LSTM2-100 leads to a mean squared error reduction by a magnitude of 1000. This may either indicate an absolute performance increase or at least better convergence properties on limited training data. In terms of further utilization of sequence history information, each model trained with a rotational history encoding outperformed their counterparts, demonstrating the benefit of sequence history information for non-recurrent and recurrent topologies alike. On the non-LIMO validation dataset, we report a reduced benefit of the rotational history encoding and time series architectures, respectively. This can be regarded as evidence for our assumption that sequence history effects like mechanical hysteresis play a more critical role during LIMO in contrast to conventional motion. The qualitative benefit of the hybrid model architecture and the leveraging of time series information becomes clearer when looking at the temporal alignment between the model predictions and the measured torques. This is particularly apparent at the inflection points in the torque profiles of joint 7, which occur at the reversals of the rotational direction. As this joint is structurally isolated from gravitational and most of the inertial torques, the torques in these joints result more from hysteresis and complex friction than anything else, which is why the time series models perform best in this case. So in summary, we introduced LIMO as a new class of dynamically complex motion that is challenging to be captured by inverse dynamics models due to the increased effect of time dependency and mechanical hysteresis. We then proposed a hybrid model architecture that provides significant improvements in torque prediction accuracy and model convergence when compared to baselines. Lastly, we showed that the use of time series neural networks and our novel rotational history encoding further increases model performance for motion with increased dynamic time dependencies, like LIMO. With this, we would like to conclude our presentation and point out that we share our code and datasets online with the community. Thank you for watching.